Hello guys, good morning everyone. Today I will be discussing the codes for both linear search algorithm and binary search algorithm. So before watching this video, you must give a look at the linear search algorithm explanation along with the time complexity and also the same for the binary search. Today, what I will be doing is I shall be discussing the code of linear search and binary search algorithm, both in Python programming language as well as in C programming language, along with the derivation of the time complexity for the binary search algorithm. So let me first go with the Python programming language. This is my PyCharm code environment. So let me create a new Python file. Okay, so new project, your Python file. Okay, create new window. New, then file, Python file. So I'm giving it a name, say linear search. So the file is created, linear search.py. Closing these previous files. So what was our first step in the linear search? Now, first of all, we actually need to declare a function, say div. Then let me give it a name, say lin search. Okay, and it will accept two arguments. For example, let me consider a list. Okay, and the target value, right? Along with this, then we will be proceeding with our code. So this is a function that will be performing our task of linear search, which is accepting two of the arguments. There is some syntax errors showing. We correct it. Target. Okay. Define linear search. Okay. And then search list target column. Then you have, let us take a for loop that should iterate throughout the list. So what was our first step in the linear search? So we will be considering a target and we will be comparing it with each of the element of the list. Okay, so comparing target with each element of list. So for I in range, from where to where it will go? So it will go from the list, I mean from the 0th index to the, say, let me take a variable named n that calculates the length of our list. Okay, length of our list. So it will go up to the size of n minus 1. So what was our next step? So this is the loop is iterating through all the elements, and now we will be comparing, right? So if target equal to list of I, okay, so we will be returning the index. Otherwise, say the loop has run throughout the list and we have found this condition was false every time, then in that case we should return -1, because that means we do not have the element in the list. That means -1. Let me write it here. So no such element found. Okay. And we can call this function with a variable. Say I'm giving a dummy list, for example, say 15, okay, 35, 20, 25, 68, 100, 90. Okay. And we will be searching for, say we can want to search for 68, whether 68 is present in the list or not, right? So we are going to print whatever this function returns on our terminal, right? If we get the index, that should be printed on the terminal. So this portion returns the index where element is found, right? So we are just in this line we are calling the function, and so for this 68 it should return, it should return 0 1 2 3 4, it should return 4, right? Because at index 4 we are having 68. And yeah, just as just calling the function won't work, we want to see it in the output screen, so we want to print and this function, right? And so run, let me run it, let's see. Right, it is printing 4. Let me give some another element and check it for it. Say I am giving 20. Okay, so for 20 it is returning 0 1 2, fine. Let me give some elements, say 150. So 150 is not present in the list, so it should return -1. Okay, and yes, so it is printing. I hope you can see this terminal window. This is -1, it is returning. Okay, so that was all about the linear search and its time complexity. As I said, in the worst case, say when I have given 150, it has compared it with all the elements. So it has a time complexity, as you know, PC is equal to big O of n, right? Next comes our binary search. The working of the binary search, as we discussed in the previous video, you should watch my binary search algorithm video that I will provide in the description box. Okay, you should, you must go and watch that video before watching this video, because here I will be only discussing the coding portion along with the working a little bit. If you watch that video, that will be beneficial for you. So let me rewrite this function. Let me create a new file named, say, binary search. Okay, binary search, Python file named binary search. Okay, binary search. Anyway, so define, say, let me give a name called bin search, that is binary search. And all it should also accept, because searching function, say user don't know what the function name is. In some cases this function name may only be search, and they are least concerned whether we are applying binary search or linear search. Therefore the argument remains same. We will be accepting a same list, okay, and a target value, and a target value where this target value, if exists in list, we will be returning that index. Otherwise we will be again returning -1. So that is for sure. Okay, so what was our first step in binary search? First, let me take a size of the list, say len of list. Okay, so this is having size of list, and as we discussed in our in my previous video, that binary search is like the page number that we search in our book. So in a book we have pages from, let's say, suppose there is a book of 300 pages. So our very first page is page number 1 and the last page is page number 300. Middlemost page is the page number 150. Okay, so at the very first stage we need to first look for the two cover pages of the book, right? Then only we can open the book. So first we open the two cover pages of the book, then we explore the book literally. So first, similarly, in case of list, we need to cover over the two boundaries of the list, right? Let me show a dummy list here. If this is the list, and the essential condition is that the list should be sorted, right, in the ascending order. Otherwise, binary search won't work. Uh, bec- uh, it's an obvious reason, because as I am giving the example of the book, even so, in book the page numbers are sorted, right? So this is a dummy list. Okay, so the first boundary of the list is this one, and the second boundary is this one. Okay, so let me take a variable, say low, that will be pointing to the index 0 of the list. Okay, so this is the first boundary of list. Okay, for books you can say it is the front cover page. Next, front cover page or the page after the content page. And the next one is the last boundary of the list. So this is, in this case, 1 2 3 4 5 6 7. So the size of list is 7, that means the last index is 6. So that means the size of the array minus 1, I is equal to n minus 1. Fine. So this is the last boundary of the list. Now, in binary search, definitely our searching space will be from the first page to the last page. And if we cross that, if we cross the last page, that means our binary search stops. Okay. So that means somehow, if this is the low and this is the high, after some point of searching, if somehow low crosses high, somehow low has crossed high, we should stop our binary search, right? So we should search only when low is lesser than or equal to high. Fine. So we will run a loop from low to high. Okay. Now, next step is to calculate the mid, that is low plus high double by 2, integer division in Python. Okay. So calculating the mid index, right? Now, so what is our first lookout? First task is to check whether we are finding out the required target or not. Say in this case, if we give a target of, let me take some more elements here. Okay, let me take some more elements, 350, 400, okay, 500, 600, etc. And our target value is, let's say, say 180. Okay. Now, so first thing is, that is our base condition. If we somehow find the element, say low is pointing here and the high is pointing here, that is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so it's a list of size 11, and the high is pointing at index 10, low at 0. So mid will be at index 5, right? 0, 1, 2, 3, 4, 5, 180. So at the first instance, we are finding the element, right? So that is list of mid. If list of mid, okay, so we will be comparing it with the mid every time, okay? If list of mid is found, that is same as the target, then we are supposed to return the value of the mid, right? Otherwise, if now say if I give a target value, let's say my target value is 500. Okay, now the game starts. If list of mid, so in this case, if you see, if the list of mid 500, I mean whatever the list of mid will be again 180 because it is low plus high by 2. So mid will be at pointing at 180 and target value is 500. So in this case, list of mid is less than 500, right? That is, list of mid is, if the list of mid is less than the target. So in this case, as the array is sorted, we surely know that as 500 is greater than the list of mid, so it will never lie on the left hand portion of the mid, right? So we can skip this left searching space, right? If we precisely see, if this is our low and here our mid is pointing and here we are having our high, in this case, in this case low is pointing here, mid is pointing here and high. So 500 is greater than the mid index element. So in such a case, we can skip the left searching space, right? Because the array is sorted. So how to skip it? That is where our searching space is from low to high. So we can extend this low one place after mid. So our searching space will be limited to this. Okay. Because we want to avoid unnecessary iterations. That is why we have discovered binary search, because in linear search we have a lot of unnecessary iterations. We check each and every element, but here we are supposed to skip the unnecessary iterations. In order to do that, this left searching space, searching in this left portion will be unnecessary, so we are skipping this left searching space. That is low is equal to mid plus 1, mid plus 1. Okay. Otherwise, if there would have been a target value, say if my target would have been 100, okay, if my target would have been 100, then in that case we would have got a value lesser than the list of mid. In that case, we should have skipped the right searching space, and for that high is equal to mid minus 1. Okay, that is all about our binary search. So how is it going to work? I am just briefing the working. So our target is 500. Okay. In such a case, 500 is greater than list of mid. So low skips 1 point. So low comes here. Okay. Mid is still pointing at 180. Okay. And low is pointing, say here. Okay. Low and high is still pointing here. Now tell me, where will be the now new mid pointing? So it's low is pointing at index number 0, 1, 2, 3, 4, 5, 6. At index 6 it is pointing, and 7, 8, 9, 10. So 6 plus 10, 16 by 2. It means it will be pointing at index 8. So 10, 9, 8. At 400 mid will be pointing, right? Okay, good enough. So at 400 mid will be pointing. So now at present moment low is pointing at 300. Okay, and high at 600. So this is my mid. Now again we need to compare with this. If so, now is list of mid equal to target? No. So this condition is false. Therefore, we go to the next condition in the if else ladder. So list of mid is less than target. Is it that? So yes, that is true because 400 is less than 500. Okay. So we skip the left this portion. We also skip this portion. In this portion again 500 cannot lie because as mid is less than again 500. So this portion is also skipped. Okay. So this searching space is also skipped. And now you just see from where the array size was around 11, and we have just reduced the searching space to only two elements, right? The searching space has been reduced only to two elements. Right? And where will be mid pointing? So it's 9 plus 10, that is 19 by 2, that is again index 9, right? So at index 9 mid is pointing. So now compare his error of mid, that is I mean the list of mid pointing, I mean the same as target. So yes, it is 500 is same as 500. So we return the mid index, and so index 9 will be returned. In this way it will be working fine. And in case we are not having the element, so say if the target was would have been 600, I mean not 600, 600 is present there, says 550, 550. So 550 is not present. In this case also two more comparisons would have been done. So low mid is not less than 550 again. So less than 550. So we will be trying to skip the left searching space. So in order to do that, low will try to go one head after mid. So low at the next stage will be pointing in the same index as high. Okay. And in this case, if this is low and low is equal to mid plus 1, so low points here. And also definitely as it is the same index, mid will also be pointing at the same index as low and high. Now think of that 600, is it less than 500 or greater than 500? I mean 550, sorry, 550. It is greater than 550 definitely, right? As it is greater than 550, the target value, what should we do? So since it is like greater than 550, we should again skip the left searching space in order to search for that. Just a second, I am doing some mistake. 500 was less than 550, so we skip the left searching space because something greater than, I mean, as the target was greater than 500, so it should lie on some portion of the right side. So in case of 600, as 600 is greater than 550, so 550 cannot lie on the right portion of 600, right? Because after 600 there will be maximum 601, 602. It is these are the possibility. So 550 cannot be on the right portion of 600. So we skip the right searching space, and in order to do that, what will high do? High will try to come one index before mid, right? So mid is pointing here at present, and high will try to come here. Okay, so high will try to come here. But now see, high low is greater than high and the loop stops. Therefore, 550 is the element we are not having in the loop. Getting my point? So low has crossed high. This is the problem. That means we are not having the element. In such a case, we return -1. Okay, that's all. So let us check for the out. So in the same way, let me call the print. I should be printing whatever this function returns. So bin search. Okay, bin search, and in that I will be passing. So let me pass this list, this whole long list. Okay, Control C and Control V. Okay, comma. So let's try out with 500. Okay, okay. So let's try out with 500. So in case of 500, our expected return should be, I'm deleting all this. Hope you guys understood by now. In case of 500, our expected index is index 9, right? So let me run it. In this case, we should get index 9. Yeah, we are getting. So index 9, as you can see. Let me try with some other value, say in this list. Okay, okay. In this list, let me pass a value. Say I pass 100. In case of 100, it should return me 0, 1, 2, 3. It should return me 3, right? So it has returned me 3. Fine. And if I return, if I type a value, say 550, okay, that is not present in the list. -1, as you can see, -1. Let me try with another value, say 360. 360 not present in the list. It should return -1 again. Very good. So, are you all guys clear about the binary search algorithm? So, this is the way it runs. And let me tell you, as I told in my previous video, the time complexity for such algorithm is big O of log n. So, I will be explaining this in this only, how we are getting a time complexity of TC is equal to big O of log n, right? Now, how we are getting this big O of log n? And this is, in fact, this is the reason the binary search is a better algorithm, because time complexity is big O of log n, and in linear search we are having big O of n. If we see, we are having big O of n. How is it? Let me derive this for you first. How we are getting this big O of log n in case of binary search algorithm, right? So just consider, initially we are considering the whole array, right? So initially low is 0 and high is, say, n-1, where n is the size of array. Okay, at the first step, okay, at the first step, we are considering the whole array. If you look at the first step, we are considering the whole array, whole list, in rather better to say whole list, right? In this list, if you see, from 0 to n, all the values are there, and we are dividing it initially, as we in the each step we are dividing it with 2. Okay, so at the first step, when the loop has not started, we are dividing it with nothing, and that nothing means 1. Basically we are dividing the list at the first step initially at the beginning by 1. So n divided by 1, and 1 can n divided by 1, let's suppose. So first step, let's say it's n. Okay, we're not dividing the list. In the second step, when we are entering the loop, we are dividing it with 2, right? At the third step, at the third step, we are dividing it with 2 to the power 1, divided by 2 to the power 1, right? Okay, I mean, very sorry, it's 2 to the power 2, because in this step we are dividing it with 2 to the power 1, right? In this step we are dividing it 2 to the power 1. Fine, because the list is decreasing. I mean, the searching space is decreasing slowly and slowly. Fourth step, n divided by 2 to the power 3, 2 to the power 3. Okay, and in this way, if we consider at the kth step, say I'm going up till, because we are not going n steps, right? We are going up to a certain step, because we are not traveling the whole array. We are skipping some searching spaces. So we may be taking some k steps. Let k be our variable. So some k steps are taken, and that kth step we are taking n by 2 to the power, because at fourth step, third step, we're getting at fourth step 2 to the power 3, third step 2 to the power 2. So in this step, we are getting 2 to the power k minus 1, right? 2 to the power k minus 1, we can say at the kth step. Okay, very fine. In the first step, we can consider, as we are dividing n with nothing, we are dividing it with dividing it by 1, and that 1 can mean 2 to the power 0. Okay, so now, and what is time complexity actually? Time complexity is basically the number of steps that we consider, right? So time complexity can be written as, because we are taking some k steps, that is big O of k. Okay. So now, but what is this k? This k is unknown to the user, right? So we need to derive something based on the size of the list. I mean the user given input, right? And you, as per the user given input, the size of list is n. So we need to bring out something in terms of n, right? So what is this k? K is unknown to the users and other programmers who will be checking our program, who will be testing our program, better to say. Okay. So let me consider this n by 2 to the power k leads to some results, leads to some constant result. Okay. Leads to some constant result, say c. Okay. Leads to some constant result c. Therefore, and we need this power below. So we need this power in the base. So we can consider logarithmic of both the sides, right? So we can write, first of all, let me take this to the right side, because it is n divided by 2 to the power k minus 1. So it is c times 2 to the power k minus 1 is equal to n. We can write, because cross multiplication. Okay. For your better understanding, you can write it as, this line is actually, let me write it for you. It's n, okay, divided by 2 to the power k minus 1. Fine. And this term is equivalent to C. This term is equivalent to C. Okay. So we get this result actually. C times 2 to the power k minus 1 is equal to n. Now we can consider logarithmic of both the sides. Okay. So log, and as per the logarithmic rule, this should come below. That is beside log, it gets multiplied. As you know, log a to the power b is actually b times log a. That I hope I don't need to tell you. Basic maths. Okay. Basic maths. So k minus 1 comes below, and it's basically, and c is multiplied already. C is already multiplied here. Fine. C is already multiplied here. So we can write this as log 2c, right? Log 2c. That is equal to log n. K can be written as k is equal to log n. Let me write k minus 1 better. Log n by log 2c. And guys, log 2c is a constant. So this constant term never change based on the user input. So that can be neglected, right? Because it will never change for any list you take at a specific time. It will give that specific result only. So this c is an unknown constant, and it's not like that we will be constant, because this is a very negligible term. So k minus 1 can be approximately considered as, it's same as log n, because n is very large, right? N can be, n is very large. We consider at the worst case, at the worst case, n is very large. So k minus 1 is approximately is equal to log n, and definitely this minus 1 is also of nothing, because k number of steps are can be very large as compared to this one. Okay, say there is a list of size 2000. So for 2000, this k will have some greater value, compare very large value compared to 1. So this 1 can be neglected, and it is k, approximately it is k. Okay, approximately it is k, and this k is basically, k is approximately to the power log n. K is approximately, approx, okay, at an approx. And what was our time complexity? Now the number of steps. So time complexity is equal to big O of k, right? So time complexity is equal to big O of k, and we can put the value of k here. So time complexity becomes Tc is equal to big O of log n. Okay. So hope you liked this video, guys. Thank you for watching this video. In the since we are very short of time, we will be discussing, I will be discussing the same concept using C programming language, right? The same code, the time complexity remains same in all the programming languages. It will not matter, just the syntax will be a bit different, syntax of writing the code. Okay, so in the next video I will be uploading the C program for the for both linear search and binary search. Thank you, guys.